Welcome to my presentation. It's about ARM PlutoSDR with custom applications. My name is Michael Hennerich, and I'm from Munich, Germany. So we heard today a lot that SDR is complex. It requires all these different kind of skills, DSP, hardware, RF design skills. But today we want to focus really on the software development side, and not just software development on a computer. So we want to run software on the embedded SDR itself. So I want to give a short introduction to the PlutoSDR system components. And since it runs Linux, I/O is a big part for us. And we then proceed in showing the autonomy of such a example code and how you run it, how you transfer it to the target. And last but not least, I want to also show how you can run GNU Radio itself on the PlutoSDR and on other commercial off-the-shelf SDR transceivers. So that's the Pluto. It's an advanced learning module. Pluto, it's also referred as PlutoSDR. It's based on a Sync 7000 DSP, FPGA with embedded ARM. It has 512 megabyte DDR3, 32 megabyte of SPI-NOR flash, and a USB on-the-go file. And it uses the analog devices 9363 as the transceiver. So what's inside? It runs Linux, and it uses the Linux industrial I/O framework to control IQ data and control. And as soon as you plug it into your PC, it registers a multifunction USB gadget. So it has multiple functions. One is native I/O over USB. The other one, it registers a serial console. On your Windows PC, it will be like COMX. On your Linux, it will be some TTY ACM. So you can run it's actually running a kernel root console on that serial interface. Then it registers remote network, Ethernet adapter, a mass storage drive for ease of use firmware updates and upgrades. And if you probe the device, it will enter a device firmware upgrade mode, and you can reflash the firmware. It also supports, it's a USB on the go. It also supports host functions. I want to talk a little bit later about that. It's also cross-platform. You can run it, you can use it with a Windows or with a Mac or with a Linux PC. So under the hood, some of you might have already seen this block diagram. There's the 9361 family. So 9361 is this, the 9363 is a subset of the 9361. It's also two receivers, two transmitters. On the Pluto itself, we only have like one receiver and one transmitter. On the SMA jacket, the main differences between the 73 and the 71 is like a little bit the tuning range, the RF bandwidth. The 73 doesn't have support for external LO. It doesn't have multi-chip sync, and it also doesn't have a tunable reference. Besides that, it's pretty obvious what's inside. Since we're going to talk about applications running on the Linux kernel, I want to show a little bit the system architecture here. On the very bottom, we see the hardware, the external hardware, the radio, the transceiver, and what's in the FPGA. So we use blocks of the Sync 7000 processing system. These are like hard blocks, the SPI controller, the GPIO controller, and then we have this AXI 809361 HDL interface core, which is a transport layer interface core that we have designed together with some DMA blocks. And on the very top, we have the software pieces, the Linux I/O subsystem. It's connected with the DMA subsystem, the clock subsystem, and so forth. And we split data and control into different drivers. So there's one driver that sets up the transceiver. That's what you use when you change the LO frequency, and the other two drivers are basically for transmit and receive. So that's a block diagram of the interface core in the FPGA that I just introduced. It's also split into RX and TX. On the RX side, we do have some matrix multiplies in there that allows you to do some IQ correction, even if it's not necessary with this transceiver, but you can still use it to do a phase rotation. Then there is some pseudo number checkers. And if you look at the transmit, there's also some pseudo number generators that allows you to actually do a loopback over the radio and back and see if the digital link runs without errors on speed. There's a bit more to it. These cores do sign extension. They provide support for, on the TX side, there's some polyphase dual tone DDS generators in there. It's easy if you just want to test something, comes out of the antenna, you can generate tone, you can generate 2 tones and just test the RF. The connectivity options are, if you plug the Pluto into a PC, it registers these 4 to 5 different USB functions, mass storage drive, Ethernet adapter, and stuff like that. But you can also use the host functionality of the on-the-go controller and plug in the thumb drive or a memory stick. That's a real thumb drive. You can also use USB wired adapters if you want to plug the Pluto into your home network, or you can use some USB dongles. So we put a couple of, we support a couple of chipsets that are quite popular, and that's also being used with the Raspberry Pis out there, and you can get them for like $5 to $15 on Amazon. In addition, you could also do some USB audio with it. Plug in a headset, or you could also use a camera, USB video camera, and plug it into the Pluto. So what is the Linux Industrial I/O subsystem? It's not just for industrial I/O. It basically supports all the non-human interface devices in the kernel. It's a sensor framework, so it's used for all these accelerometers, gyros, sensor, all kind of sensor types. And it's in the upstream Linux kernel for more than 10 years now. So why do we use I/O for software-defined radio? So first of all, we said we want to use Linux because it's a nice ecosystem, and it's actually also part of the Xilinx ecosystem for the Sync 7000. So it was quite obvious for us to use Linux. And then you could put stuff in user space and create a user space driver, or the better approach would be to create kernel drivers. And the kernel drivers do have a couple of advantages, because kernel drivers have low level and low latency access to hardware, to memory mapped peripherals, interrupts to DMA in memory. There are workarounds. You can also put stuff in user space, but then you take always the system call latency whenever you do a byte transfer, or you want to get a buffer or something like that. So I/O provides a very good abstraction layer, which allows sharing of infrastructure. Developers can focus on a solution, and it also allows application reuse. So you use this to create one application, and if you move to a different transceiver that also has an I/O driver, you don't need to change your code, your user space code at all. Maybe a little bit, but the concept and the things are all the same. And of course, I/O provides very fast and very efficient support for moving data from the device to the application, vice versa. And also, the kernel has a lot of what's being called zero-copy facilities, where, for example, a buffer can move directly to the Ethernet interface and being sent out without manual copy process and stuff like that. So I/O devices, an I/O device is like the top level unit in the I/O world. In general, in Linux, there are buses and devices, and a device typically corresponds to a physical hardware device, an ADC, a DAC, or an amplifier or something like that. And all these things are represented in a virtual file system, the SysFS file system, which is under sysbus I/O. You see the devices. Each I/O device has attributes. Attributes describe hardware capabilities and allow you to configure things like, let's say, sample rate or gain or power down. And also attributes are just files in a virtual file system. A device can have multiple channels. A channel is the representation of a data channel and has a direction, whether it's input, output, it has a type, whether it's a voltage or whether it's a temperature or a current. It has an index because you can have multiple channels and also modifiers. For example, acceleration would be measured in X, Y, and Z dimensions. And if you look at IQ data, it would be I and Q modifiers. Also, channels can have attributes for things like a frequency, a offset, a raw value, a hardware gain, stuff like that. So that's an example how you would control a variable gain amplifier in the I/O world. There's a device. A device has two channel attributes. It also has a device attribute, the name. And you would just write a value. You echo a value into this file name, and then you can cut this file name, and it comes back with the value that's actually written to the hardware. You ask for 6 dB. The driver says 6 dB is not possible, but I take the closest, which is 5.76. I/O devices can also have buffers, and buffers are used for continuous data transmit and receive. In a buffer consists of a set of channels that can be enabled or disabled. So you can say it's a 2RX. I just want to have I and Q from the first channel, and then you turn off the other two channels. Also, buffer describe their data layout. So what's inside the buffer, whether it's like signed, unsigned, little endian, big endian, how many bits, and things like that. Again, everything is configured by SysFS, and there are different buffer implementations. For SDR, the typical thing is a DMA buffer because everything needs to be really fast and with very low overhead. And the DMA buffer basically uses direct memory access to transfer data between the device and the memory. And once it's in the memory, and in user space uses something that's called mmap to map the physical memory into the virtual address space of the application. And it's not a copy action, it's basically just some pointer action. So there is the MMU which takes the pointer, gives it to the application, and it magically maps this block into the application's memory space. And this allows very high-speed data capture. Also, in terms of terminology, data is grouped in chunks, which are called DMA blocks, and the I/O framework manages the ownership of those blocks, which are either in the application or in the kernel space. So, for example, they are filled by the DMA, and then the application receives the block once it's available. So, I/O itself, the kernel API is a lot of things like writing files, reading files, opening files, doing I/O controls on files, which is not something a typical developer would expect. They want to have a function call API. They want to call a function and don't want to really open the file descriptor and write some strings. So libIO closes this gap. So it really focuses on ease of use for handling I/O devices. It provides several language bindings, so there's support for C, C++, C#, Python. And so everyone can write his I/O application in its favorite language. So there's an example for Python. You import I/O, then you create a context, and then you just loop over all the devices and print their name. It's available as Debian package, RPM package. It's a layer and open embedded. It has Builtroute recipes, so it's pretty widely adopted. Backends. So the concept of libIO is that you have a local backend and that you can also have remote backends. So you can write your code on your PC and just say, I want to use the network backend, and it connects to the radio, which is over here, over a network link. It can also be a USB link or a serial link, or it even might even be like a PCIe Express interface. So backends are totally transparent from an application point of view. So it doesn't really matter. So maybe we advance on this slide. Here's an application on one computer that uses the local backend, or you can have an application on a different computer which uses a network backend. Also, this slide is about IOD. That's the daemon that actually makes that happen. So the daemon runs on the target, on the SDR itself, and provides this kind of connectivity to other applications who might sit remote. With libIO, there are a couple of tools, IO-info, IO-attribute, which allows you to manipulate, read and write attributes of channels, or in general of all of devices. Then there's a tool readdef and writedef, which is basically used to stream data to or from the device. So you can, a basic loopback over here, readdef, and then pipe the output into writedef, which is a loopback. And then there's another tool, it's called IO-reg, that allows you to manipulate device registers. So custom applications. So this is a very simple libIO examples that shows how to control a 9361 or the PHY, the transceiver on the Pluto, or even on other devices that use I/O. So the first thing is you create a context. And the context can be created from an URI, which can be either local. That's when your transceiver really sits local in connected to your CPU that you're running the code on, or it can be just an IP address, or it can be a USB URI, or a string that identifies a serial interface. Then you find the device. All I/O devices have names. In this case, it's 9361 PHY. Once you have the device handle, you can use the device handle to write channel attributes. So you need to find the channel. In this case, we look for out voltage 0, which is the RX synthesizer. And you write the frequency attribute with 2.4 gigahertz. And in the line below, we do the same thing just for sampling frequency. So in this example, we change the LO frequency and the sampling frequency, and then you possibly want to move some data around. That's what receive does. Receive, as I showed earlier in one of the slides, that we have different drivers, a PHY driver and then 2 drivers for transmit and receive. In this case, we get the device that's called Core FPGA 809361 LPC. We find some channels, voltage 0, voltage 1, which correspond to I and Q in this case. Then we enable the channels. Then we create a buffer with a certain size. And then we just call IO buffer refill. And then we get the buffer step and where the buffer ends. And then we just loop over the buffer and get the I and Q samples. So some system considerations here. The buffer handling sizes and counts. The buffer size is typically set to a chunk or a suitable frame size for your application. Sometimes it's like n times FFT size. There are some considerations. Small buffers are less latency, but more overhead, while big buffers are less overhead, but more latency. In the I/O world, you can set the number of discrete kernel buffers. Those are the buffers that are in this queue mechanism that are being filled at the same time while you consume them. And if you have some latency sometimes that you need to accommodate, you basically increase the number of buffers. Also, as soon as you create the buffer, the kernel starts filling them. And the whole implementation I/O is that it is a FIFO-like behavior. And that means that new data is dropped. So if you can't consume the buffer in the application fast enough, new data is being dropped. So in order, sometimes people just looking for, they want to have like 20 milliseconds of LTE-20. And they can't process it fast enough because it's 30 megasamples, and it's not something that they can process. So they want to increase the buffer sizes. And there is a limitation, which is set by the max block size parameter. You can change it. The default is 16 megabyte, but you can also set it, let's say, to 64 or 128, which you run then into this problem. Linux uses a contiguous memory allocator to allocate big blocks early at boot time. And there is a limit. But the limit can be changed. For example, on Pluto, we set the limit to 256 megabytes, but you can even increase that further. That's the amount of DMA-able contiguous memory that's available to your system. And if you start filling these big buffers, maybe potentially pretty slow, you may run into an I/O context timeout, which can be disabled or can be increased. It's just a pointer because people sometimes run into these things. The Pluto has a firmware, and everything is open. Everything is open source. And that's just a small recipe how you build the PlutoSDR firmware image. You install some build dependencies, clone a repository, set up some variables, environmental variables, and then type make. That's how easy it is. The Pluto itself uses a Builtroute for its user space. And it is like something like Open Embedded, or there are different kind of embedded Linux distributions, and one of them is Builtroute. So you can customize it, you can enable tools, libraries, packages, and that's how you do it. And inside, Builtroute also has the option to use BusyBox. BusyBox is the Smith Army knife of embedded computing. It's a big collection of Linux commands that are really small in size. And that's how you customize your BusyBox. Type make BusyBox menu config, and then again copy the configuration file to a location where it's being used. If you just want to add your own application into the Pluto SDR root file system, you can just copy it into the staging output folder, and then just type make. Next time you make clean, all this is gone. So you want to have a way how you permanently add those files, and then in the BusyBox world, there are two things: post-build scripts and file system overlays. One is a script which says copy this file to this location every time, or a file system overlay is a folder structure where you can put files in, and then they are at the end of the file system creation copied over the other file system folders. So if you're not interested in rebuilding the PlutoSDR firmware, you just want to compile your own application and you want to run it on the Pluto, that's also easy because we provide the Swissroot for every firmware release. The Swissroot is basically the library files that are being deployed to the Pluto, that are in the PlutoSDR firmware root file system, and where applications link against them. We provide a copy of them for your development PC, so you can link applications against those libraries and then copy them over to the target. So how you would copy an application over to the Pluto? The first thing, you customize the file system, but then you need to reflash the firmware. That's not something you want to do always. The other option is just to use SCP. That's an SSH tool. It allows you to copy a file or a set of files over a secure connection. The password is analog, and there are also some how-tos on how to avoid typing the password over and over again, and there's also the secure key changes every time you reboot the Pluto. That can be quite annoying, and there's a link to how you need to modify your SSH config on your host in order to not get those annoying warnings. The other thing is you can plug in a thumb drive, so you copy your application to that thumb drive, and then there is a mechanism. As soon as you plug in a thumb drive, it automatically gets mounted. There's an auto mounter, and then there's a script that runs on the Pluto that looks for files that are named like runme, some number, and those files are being executed. So you can type in shell commands. It's a bash or shell script. So you can run lots of different things in there then. That's the example, how you would compile an application. That's an example where we download dump 1090. That's an ADSB receiver. So first we get the Swissroot from the firmware releases. Then we untar the Swissroot. Then we clone the dump 1090 application that we want to build. And of course, again, that's the clone. And then we compile the application. So we give the the CC is the compiler name, and then we pass in Swissroot equals current path up to one directory staging. That's the directory that comes with the Swissroot. And once you've done that, you copy over the application to the target. And we did that here on the serial console. As I said, you plug in the Pluto, it registers the serial console. You just then dump 1090-net, and then you can use your favorite browser, type in the IP address of the Pluto, and it gives you this user interface where it looks out for, it receives the ADSB frames and looks for the flights, altitude, speed, and puts it onto your web browser. As I mentioned before, you can also run GNU Radio on the Pluto itself. There are only 32 megabytes of spine NOR flash. That's way too much for GNU Radio. The workaround is to just use some ARM hard float userland code. Linaro provides that. There are tarballs. You copy it over to a thumb drive. In order to use that, you need an X4 file system support in your Linux kernel. As soon as you plug in the thumbstick, the auto mounter, you put in a script which basically uses the busybox switch root command, and switch root does nothing else than a change root. And then you would change your root file system from your current PlutoSDR root file system to the root file system that is on the memory stick, and then you execute the init process on the memory stick. So you basically change your root. And it then automatically launches the Ubuntu system where you can just use apt-get install GNU Radio Companion, and it downloads tons of stuff, but it works. Yeah. As I said, there are other devices that can also run this Linux I/O system. For example, the Sidekick Set 2 has support. For those who haven't seen it, the Sidekick Set 2 is a pretty neat small radio that is in a mini PCIe form factor. It uses also the 9364, but in addition has some LNAs and RF filtering on it, and a very good high-precision reference clock. So you can build a firmware blob for this device with the PlutoSDR repository by just, in addition to make, you set a variable, it's called target equals Sidekick Set 2 and type make. Also, we added support for the Atmos III10. What's supported is that we support the RX and TX filter banks and switches, USB, Ethernet, real-time clock, all this stuff. What's currently missing is soft power down because it's a bit complicated to actually use it the way it is implemented in hardware on the E310. So in order to shut down the device, you press the button really long, and then there's some hard shutdown, which is part of the power management. Also, we don't have support for synchronization with the pulse per second time reference. Here's some pointers where you find the HDL, how you build the HDL, where you find the kernel driver source for the E310, and the kernel config and device tree files. Also, in addition, Analog Devices provides a lot of reference designs for all kind of Intel or Xilinx carriers, Area 10, Cyclone 5, SoC, Virtex, Ultrascale, Kintex kind of platforms. Even like we also support this on the non-SoC versions. For example, VC707 or KC705 don't have a hardcore. And we have a couple of FMC cards for different transceiver families, the ADRV 9009, 9371, and the 9361 family. So you can use all what I've just talked about also on these carriers with these FMC cards. For support, typical Pluto questions should go to the Engineer Zone university community. Then we have two more forums, which are more on the FPGA side and on the driver side. And of course, there's also an I/O Linux kernel mailing lists. Thanks for your attention. And we have two workshops. One is about the Pluto itself. It also covers a few things that I discussed here. And then there's another workshop about system programming that Travis is giving later this week.
Thank you very much. We have time for just one question while we're swapping over the slides. Would you mind?
Yeah. Do we have any questions from the audience? No? No audience questions? Oh, we have one. Here you go.
Just for clarification, there was a mention of the OTG interface. Does that support like a USB hub for if you wanted to,
Yes.
like
You can plug in the hub
and put multiple devices on it?
Yeah.
Okay.
Great.